Thank you, everybody. I'm very excited to be here. And also, I'd like to thank the organizers for giving me this opportunity. And I couldn't think of a better introduction to my talk than the previous great talk, which poses the questions why, and causality, and also like hints at the standard tools for feature importance and all of that are wrong. So let's go. So this is my conflict of interest declaration. As we heard, the previous talk, AutoML focuses a lot on hyperparameter optimization, but it should be much more than that. In the industry, it's much more than that, and clients care not just for the model and an AUC, but things about prediction estimates, what are the important features, quote unquote, the explanation, the role of the selected features, and why not the causalities, all right, and many more, but I'm going to focus on the green fonts today. So, feature selection, what is it, why we do it, how we do it? Sometimes feature selection is the primary task in our analysis. You won't believe it, but the client doesn't want the model. They don't care about the predictions. They care about what are the important features because they feel intuitively that's what matters for the causality. Is this well-founded? Yes. We'll see the theory, and you see the reference over there. We'll get into it in detail. So feature selection is our main task for knowledge discovery. Let's see a little bit more now how exactly we can define that. I'll partition into two problems, single feature selection and multiple feature selection. In the single feature selection, we want to find one minimal set of features that collectively carries all information for optimal prediction. So minimality, you want to throw away irrelevant and superfluous, redundant features, jointly examine them, and you don't want to lose important features. So for example, you may have this type of data. The names are really weird. They are from bioinformatics. You may discover an optimal algorithm that these two features lead you to an optimal model. That's great. But in multiple feature selection, we try to find all such features. Feature sets, I'm sorry, because there may be another set of features that leads to an equally good model. And this is an important problem that's going to unlock our understanding about the problem. It's misleading to use a feature selection problem with an algorithm and then go to the doctor, to the biologist, to your client, to whoever, and say, look at these features only, all the rest are non-important. Okay, but single feature selection suffices for predictive purposes. For knowledge discovery, for understanding the whys and the causality, we need also multiple feature selection. All right, and to define it properly, I'm going to remind you or introduce to you the concept of conditional independence. You see here the definition, basically what it means, and the notation I'm using. Basically what it means is that if you have selected, let's say, features Z, then X becomes independent of your target Y. It gives you no additional information. It may be giving you information by itself, but additionally gives you no information. And what can happen, some weird statistical phenomena, is that you have selected some features, X doesn't give you additional information, you select more features, now X becomes dependent, gives you more information, then you select more features, now becomes independent. So it creates a combinatorial problem that, in the worst case, it's NP-hard. So defining the feature selection concept mathematically is that we're looking for a minimal size subset that makes and renders all other features independent, jointly renders them independent of your target, given the selections you have made. And such subsets in the causality literature are called Markov boundaries, all right? Markov boundaries by Yuda Perl, that's who got actually the Turing Award for this kind of work. Now, in the multiple solutions, we are looking for all such subsets, all the Markov boundaries, all right? And in finite sample, you may have feature subsets that lead to models that are equally predictive up to statistical indistinguishability. So now that we understand a little bit like and acknowledge the presence of multiple solutions, we can define the following taxonomy of features. We can have 4 types of features. Features X that carry no information for T no matter what you select. These are irrelevant. On the other extreme, you have features that you absolutely need. They're in every Markov boundary, in every solution. You need them to build optimal models. They are called indispensable. Then you have like features that belong into some solutions but not in other solutions. And what this means is that you could replace them with some other features and get to an optimal model. So let's call them replaceable. And finally, you have features that don't belong in any solution, meaning like, but give you information for your outcome, depending on what else you select. But you don't need them in an optimal model ever. So these are redundant, okay? So in multiple feature selection, we would like to throw away the irrelevant, we'd like to throw the redundant, and I inform the user that, these are the indispensable, these features are replaceable. And to be more specific, if A can replace B in a model, they're informationally equivalent with respect to Y. We can group these informationally equivalent features, let's say A and B and C, if one can replace the other in a final model. And of course, you could have, this is a limited version, you could have a whole set of features replacing another set of features in the general case. All right, so now, all right, we can explain some interesting phenomena here, like instability in feature selection. So you do your cross-validation, and let's say you have A being informationally equivalent with B. So what are you going to find? You're going to find that sometimes A is selected, sometimes B is selected, all right? Or you do your feature importance using random forest, very common, very wrong. Because let's say you have an importance of 50 when you just have A, but now you have informational equivalence and multiple solutions. This 50 is distributed to all the informationally equivalent features. So if you set the thresholds and you say, I'm going to use the first K features, you may be throwing away both A and B, all right? Instead, we want to keep one and only one of them in the final solution. All right, so this is a theory, and we acknowledge multiplicity. We need to solve the multiple feature selection problem for knowledge discovery. Now let's see how feature selection actually connects to causality. Can it answer the questions why, as it was posed before? But in order to do that, I have to give you a little briefing about causal models, and specifically causal probabilistic graphical models. Like this one, this is actually built by a domain expert, and usually, obviously, we want to build them from data, and we don't know the true model. In this case, in these models, edges represent direct probabilistic causal relations, meaning direct, meaning nothing intervenes this causation, and the graph is accompanied by parameters, all right, to do quantified predictions, but let's not worry about this at the moment. And obviously, the true graph is unknown. But let's suppose we do know the true graph. What's the solution to the feature selection problem? What are the features that are optimal, let's say, for predicting this variable? All right, let's answer this question. So, but before we do that, very quick introduction to some key important causality concepts. A collider is, when you have a path like that, Y is called a collider on the path. Could be collider on one path, but not on the other. It's a common causal effect of both X and Z. You see the edges collide. And a collider path is a path where all intermediate, but also observed nodes are colliders. All right, so trivially, a path like this with a single edge has no intermediate nodes, so it's trivially a collider path. This is a collider path. This is a path with 3 intermediate nodes, two of them are colliders on this path. And if I assume that I don't measure L, so it's not an observed node, then it's a collider path. Okay, and then another concept that's important is the concept of confounders, confounding causes. So we see here Y causally affecting two variables, X and Z, and mostly we care about latent confounders. These are the problematic cases. And then another important concept, which is the faithfulness condition, that our causal graph gives rise to all the independencies and only those independencies that you see in the data. You don't have independencies in your data that are basically due to fine-tuning of the parameters or some accidental property of the distribution. Causality creates independencies and nothing else. That's deep, but I don't have time to go in all depth today. So let's assume we have a causal model like that, and it's a DAG, no feedback cycles, but it may have some latent variables that you see here in squares. Here's what the theory tells us. It tells us that, first of all, the Markov boundary is unique. That's good. So no multiplicity of solutions, no replaceable features. And also the Markov boundary of Y are all nodes connected to it with a collider path, via a collider path. So for example, these nodes are connected to make model with a collider path of a single edge. Same thing for these ones, the green ones. But also this node, it connects to make model through this path. This one is an intermediate node, it's observed. This one is an intermediate node, but latent. This is an intermediate node, and observed, and it's a collider. So this is a collider path. So this is the theoretical solution to the feature selection problem. All right? Now, so an optimal feature selection algorithm should return, given the data, this thing. Now, if additionally we assume no latent confounders, then our data can be represented with a causal Bayesian network. And this is what people mostly use. And when you use something like that, whether you want it or not, implicitly or explicitly, you are assuming no latent confounding factors. All right? Whether that's, just be aware of that. And the second thing, and in that case, the Markov boundary is simpler. I mean, it's just like the parents, the children, the neighbors in general, plus the only confounding collider paths you can have are to nodes that are called spouses. They are the direct causes of the direct effects. Okay, so it's a little simpler. And then if we have if our target is a terminal node, this node here, that comes temporarily after we observe everything, then the only things that can be the solution to the feature selection problem are the direct causes, all right? The direct causes. So in that case, really, feature selection is going to give you the direct causes of your outcome. All right, so the causalities determine the solution to the feature selection problem, and an optimal feature selection algorithm should return the Markov boundary, but we won't know the directionality of edges. You need additional inferences to figure out the directionality of edges, if you can, and explains theoretically really why feature selection is or should be used, or when it could be used for knowledge discovery. And for us, it has inspired us to develop new feature selection algorithms and be able to prove their properties using this theory. And I promise you, if you actually spend the time to read about causal modeling, it will change your view of data analysis forever. So constructing feature selection algorithms now and putting all this to practice, we need algorithms that are general and they can run on any type of data if you want to have a commercially successful product. Algorithms that scale up with a number of features, and they scale up to millions of features, because we work in biology and they measure millions of features sometimes, yes. But also, if you have feature constructors, let's say from relational data, okay, with relational data, you can actually construct an infinite number of features sometimes. You have cycles in your schema. Or other feature constructors, they end up like with hundreds of thousands of features. We also want to be able to scale either up or down with sample sizes, and also scaling down to very few tiny data sets is important in many, many applications. And finally, return all solutions, if possible. These are our desiderata. So let me move on here. Like, these are some advances that we have made, like in feature selection. And in our tool, we also use some of these algorithms plus some standard algorithms. And as you can see here, like some of them can run on any type of outcome, including time to event. If you want to predict churn, if you want to predict failure of machines, that's what you need. They're censored outcomes. Here are my recommendations when to use the algorithm in terms of like how many samples you have. Some are designed for very low sample size. The heuristics they use like really don't create big models, intermediate models to require a lot of sample. The number of features they can extend to, and the theoretical properties, meaning do they return always under some conditions like the optimal solution, the Markov boundary, or a subset or a superset and things like that. All right, and you can find actually, of course, we have in the commercial product, but some open source like implementations are in the R package MXM. I know, I hired a statistician, he built a package in R. Apologies. All right, so now let's see this in practice in our tool called Just a Data Bio or JADBio. You know, we created with having in mind like bioinformatics applications with tiny sample sizes, lots of features, but of course doesn't run only there. It evolved like it's the third generation of our tool. We built the first one back in 2003, 2004, called Gene Expression Model Selector, GEMS. I think it was the first AutoML system. We had to also invent like nested cross-validation to provide unbiased estimates of performance. If you know, for the history, you know, if you know a system like that comes earlier from that, please let me know so I can properly quote it. Then we developed like a BioDiscoverer, which was a plugin for another tool, and then we had like our JADBio was a third generation product, and now it has led to more than 40 scientific publications with discoveries from that. And also this history tells you like how bad I am at marketing things, right? Because I didn't coin up like the AutoML term, which is pretty good like for popularize all this. All right, so JADBio, like you can find it at jadbio.com. You can get like a 14-day free trial for the full product, and then it's the basic version is free forever. But if you're doing research and we can help you, just send me an email. I'll be happy to do that. And it runs on nominal, continuous, but also time to event like outcomes for different feature types, including images as input. It can handle repeated measurements and sample sizes up to down to 15 per class. Okay, so it can run with tiny like data sets and scales up like 2 million of features. It has an API and so forth. All right, here's how you can run it with a GUI at least. You upload a data set by drag and drop. And then you click next a few times. Here the data set has 500 columns plus, but each time you see 5 in your screen. You select the outcome, and then you click next, and you do the analysis. And then you get to see the results like in detail. Here you can get the model and plug in, it has selected 5 features. You can plug in like different values and get a prediction. In this case, it's binary classification, so we get like as a prediction the probability of the 2 classes. And then we get to see like results about the model, like AUC curves, ROC curves, AUCs, different other types of metrics. And finally, what I'm talking in this talk, the selected features, all right? Like here, we get to see selected features and information about that. All right, let me show you a little in more detail the output. As you can see, this is an example from trying to predict COVID-19 severity with about 35 transcriptomics measurements. The AUC is pretty good. Also, the AUC on external test set is pretty good. And JADBio selects like 18 out of about 35,000 features and finds two such subsets of 18 features that you see here as signature 1 and signature 2. And they're exactly the same, except that feature 16 can be, you have two choices. You can like substitute this with this feature in your model and still get like an optimal like performance. And when you try to explain the role of the features to like practitioners, we use what is called a nice plot, or at least a version of a nice plot. I can't recall what it stands for. Anyways, you see here that on average, the prediction of the model increases with increased like values of the feature value, the measured like value for this feature. So an MD would call this a risk factor, you know, because if it's high, like you probably have Alzheimer's. Risk factor, you know, they hide behind this terminology so they don't express or commit to causality, you know, but in the back of our heads, we would like to figure out if this is causal, right? And also in gray here is the range of predictions that you get because of the values of the other features. So the information that I get is that when this is high, no matter what the other features are, the predictions that you have Alzheimer's. And when this is low, anything goes. The prediction really depends on the other two values. And after you remove redundancy and multiplicity, then you can show a feature importance, because now you have removed the informationally equivalent features. And we show this in the estimation of the predictive performance drop with relation to the original model if you remove a single feature at a time. So if you remove the first feature, your drop is 8% with these confidence intervals. All right, so let's see now some applications. Here's a wide evaluation of JADBio against TPOT, TPOT MDR, Gamma, AutoScikit-learn, and Simple RF on 360 data sets, and that was published in Nature's Precision Oncology. Basically, this is the difference between the out-of-sample AUC on held-out data, and this is the ratio of features selected with respect to the features selected by JADBio. So in conclusion, basically, we reduce the number of features that you need about 4,000 times with respect to the other tools, usually selecting less than 20, most of the time selecting less than 20 features without a significant drop in the performance. Here's some work, undergoing work with the NASA Gene Lab, where they have two data sets from different like types of related types of cancer. And each data set results in two signatures or 4 genes, 4 features, where we see here like the 2 signatures, and in one data set, the 2 signatures in another data set. Then we tried like the model from one data set and tested it on the other and vice versa. And we get like excellent AUCs, so the models do transfer. And also when you plot these nice networks from that connect like the identified like features in the centers with what we know about the biology, there's some like you cannot see, there are some connections between all of this, but anyways. That gave a very nice interpretation story to the biologists. So the point is like that we don't overfit since the results transfer to external data sets. Now let's go to genetic data, where we try to predict the height of adults from their genetic variants. We have like around 7 million of them and relatively few sample size. And we were able to identify 50 features that get you up to like 0.45 R squared. And The state of the art on this is 0.53, but they're using lots of prior knowledge. We do the discovery of these SNPs, as they're called, these variants like de novo. And also they use like, I think, 2,000-3,000 to reach this performance. Okay, so the point is like, yes, this feature selection scale to millions of features, but also without overfitting. Now, how do you shield against overfitting? That's another talk that I don't have time to go into today. All right, these are from the same paper, applications like on other, as they're called, genome-wide association studies with millions of like SNPs. And what they still do in genetics, is like select genetic variants based on their univariate association with the outcome, all right? So you see like how low performances they get versus to do it like multivariate with state-of-the-art like AutoML. Okay, microbiome data analysis. Can we predict a bunch of like diseases from microbiome data? So these guys did the literally dirty job of collecting microbiome samples from human intestines, all right? And you create like 12 million features out of that, like about the different microbes that they can be there. And we were able to like identify 100 of them that give you an average AUC of around 0.84. And also our clients that you see here, some of our clients that you see here have identified like features, biomarkers that now they have are in the preclinical trial for drug development. So hopefully we'll have like some drugs that are developed based on these like discoveries. Okay, so all right, to summarize, feature selection is the primary task in many applications. Don't think your job is over to a client in the industry because you delivered a nice like model with high AUC. Feature selection is intrinsically connected to causality. And it's not as trivial in saying, you know, like the features selected are the causes. No, I mean, we've seen like some conditions that has to hold for this to be true. Multiple feature selection is there. You should be aware of it. So you can interpret like feature importances correctly. And it also explains instability of solutions and things like that. Now, in terms of like what we've done so far with JotBio is we have developed techniques for general feature selection applicable to any type of outcome. It's scalable and also scales down to very few samples. And some of the algorithms, not all of them, return multiple solutions. And we have robust implementations in the tool. And also, if you do it right, there are many tricks to do it right, like that I describe in papers and other talks. You shield yourself against overfitting, because it's very easy with that many like features and tiny sample sizes. But now, what's next is to move on to automating causal discovery. So, you know, like piecing together the whole network, identifying like the directionality, identifying the presence or potential presence of latent confounding factors, figuring out like all the causal models that could fit the data, explaining results to you know, people without a PhD in causal discovery and all of that. So we just started, and hopefully soon we'll have like some results. Okay, so I would really like to thank again the organizers, the JotBio, and my academic team that I call MXM. You can find more information on these websites, and if you want to learn more, like, please contact me, and I would encourage you to like use the system and give us some honest feedback, or maybe you want to do some research on it and the like. All right, so thank you very much.
All right, thank you very much. We can have a couple quick questions. And And also, can the panelists for the next session come to the stage?
All right, thanks very much. That's super cool stuff. I should briefly comment on the first AutoML tool thing, because a lot of people in the room would probably have sort of learned AutoWeka was something really early, 2013. And I've definitely gone away from saying AutoWeka was the first AutoML system. Still, a lot of people think that. I should give some credit to a particle swarm model selection that was in 2009, so after your stuff. But at the time of writing AutoWeka, we didn't know about that. So Hugo Gera Escalante, I would like to call out. Yours, I did not know about until today. Awesome, 2003,
That's
2004.
why I'm saying I'm really bad at marketing.
And I've also gotten feedback from RapidMiner. In 2002, they had a grid search over the entire chain of operators. So they said that could be viewed as an AutoML system. I think it's all shades of gray.
Yes.
But it's still important to acknowledge these early references. So awesome that I just learned about yours, and there is so much cool new stuff we should talk about. Thank you.
Thank you. Thank you.
Yeah, thanks for this very inspiring talk. Maybe this is going to be a stupid question because I'm not into causal modeling, so sorry for that already. So if you do these causal models in order to do this multiple feature selection to find basically all relevant subsets in a way, I was wondering, like, do kind of things like fuzzy systems and those stuff play their role? So what's the uncertainty of then maybe finding these causal relationships and so on?
Yes. So how do you handle the multiplicity basically in causal discovery? And here's the deal, like I have not seen a single algorithm, including mine, that handles multiplicity in causal models. So they don't. Basically, they try to find the best causal model with a single Markov boundary. And most of the algorithms assume like faithfulness. So if you assume faithfulness, then there's only a single solution. There's no multiplicity. But even if faithfulness holds like mathematically asymptotically, with a finite sample, there are multiple like subsets that you cannot be sure about which one is better, which one's the true Markov boundary and not. So that's great kind of like direction for research. And fuzzy sets could be one direction to solve it, maybe. Yes.
Okay. Thanks.
One more?
Okay.
Okay, thank you for the talk. I had one quick question. You always mentioned that feature selection in your case scales to like this millions of features. Could you give us numbers how long it actually takes in minutes or hours or?
How long it takes?
Yeah.
I mean, if you want to like go to millions, yeah, a few hours.
Okay.
Okay, but I mean, it also depends. Is it a binary classification? Is it like a multi-label? So multi-label takes much more. That's one. So it has happened like that. It takes days, and also depends on your sample size. If it's very imbalanced, then okay, maybe you have like a lot of sample size, but maybe one class is very rare. So what we do is like thorough cross-validation and sometimes repeated cross-validation to reduce the uncertainty. So that like makes things more time-consuming. But if you have like very balanced data and a lot of them, you will just do a holdout, right? These are all automatically determined, by the way, like by the system. So it really depends. A few days to maybe an hour or minutes.
Thanks.
All right. So I'm staying here for the.
Yep. Let's.
Well, thank you, everybody.
Yeah. Thank you very much once again.